Welcome to Module 29 in this series of lectures on statistical process improvement and statistical quality assurance. We return to the topic of Shewhart control charting, now discussing control charts for counts. We're going to, or in the old time language, attributes data. We're going to do this in two parts, and this is, of course, the first part. We're going to discuss in this module Shewhart control charts for quote-unquote fraction conforming, and in the next we will discuss Shewhart control charts for mean conformities per unit. In this module we'll talk about so-called P-charts and NP charts. In the next we'll talk about U and C charts. I should begin with a disclaimer here. These tools are really very easy to use and explain, but in all honesty, the control charts for measurements are almost always more effective than control charts for count data, and for that reason these are discussed not first here, but after X-bar charts and S charts, but these are nevertheless still in common use, and so we should learn the language and the motivation and the application of these charts, recognizing though that they're not as effective as the charts we've already discussed in typical applications. That's particularly the case when acceptable nonconformity rates are in the parts per million range. These charts are just useless in that context. Okay, so we're going to talk about charts for quote-unquote fraction nonconforming. The scenario is this, that one takes a sample of n items or process outcomes and counts up the number of outcomes among those little n that are non-conforming. Non-conforming in old-time language you might say defective. Non-conforming is the more modern usage, both recognizing that sometimes things that are non-conforming are not defective in the sense of being non-functional, and so that's one reason to use this language. Another reason to use the language is simply to avoid using language that has legal implications, like the word defective would. In this kind of a circumstance, we're going to use the notation p hat for the number nonconforming in the sample over the sample size. That's a sample fraction nonconforming. If one plots and charts this sample fraction nonconforming, then the language is that one makes a p-chart. If one plots the number nonconforming in the sample, simply x alone, then the jargon is that one has made an NP chart. As a probability basis for control charting, a review of elementary probability in statistics should tell one that a sensible probability model for this number nonconforming x is the binomial distribution, where number of trials is the sample size and the probability that any particular outcome or item inspected is non-conforming is this number p. If you review your basic probability and statistics, you will come to the conclusion that the mean for a binomial distribution is n times p, And the standard deviation for a binomial distribution is the square root of np times 1 minus p. That means if one divides a binomial variable by n to make p hat, the mean and the standard deviation for x get turned into mean and standard deviation for p hat by division by n, and that produces a mean of p hat being p, a standard deviation for p hat being the square root of p times 1 minus p over n. These facts then in turn lead to standards given control limits for x that are mean for x minus 3 standard deviations for x. For the lower control limit, mean for x plus 3 standard deviations for x. For the upper control limit, and if one is not doing control charting for x but rather for p hat, essentially those limits get divided by n and become these. Here are some artificially generated data based on a fraction non-conforming of 3%, 0.03, sample size of 400, except for sample 9, where a larger value of p was used. So this that sample came from a different binomial distribution, but the other 19 are from binomial n equal 400, p equal to 0.03. And if one was going to do control charting for p hat here, making use of the standard value of 3%, the lower control limit for p hat is going to be 3% minus 3 square roots of 3% times 97% over 400. That's this number. And the upper control limit for p hat, there's a addition instead of a subtraction to give a upper control limit of 0.0556. If one plots the fractions non-conforming against the sample number with a center line at 0.03, what one sees is that only sample number 9 produces a p hat that's outside of control limits, but that value of p hat is simply too big to have sensibly come from a stable process with p of 0.03, and so we have evidence in the data that indeed what I told you was true about how the data were generated. That can be seen in the data. This 24 that turns into a 0.06 is simply too big to have come from that value of p with n of 400. Retrospective control limits for x or p hat are obtained by taking the standards given limits and making a provisional assumption of process stability, making an estimate of p, and plugging that into the standards given limits. Here's the typical way to do that. One takes the total outcomes that are non-conforming or total items non-conforming and divides by the total number of outcomes observed. That amounts to adding up counts for, say, R samples and dividing by the total of the R sample sizes. That is a weighted average of p hats when in fact the sample sizes are all the same. That turns out to be exactly the arithmetic mean of p hats. But it's probably safest to think of this pooled S in the form total outcomes non-conforming divided by total number of outcomes. If you return to the artificial data on panel 6 and count up the total non-conforming, you get to 246. Sample sizes were 400. There were 20 samples. That's 8,000 outcomes. And so a pooled estimate of a single P for that whole set of 20 outcomes, assuming that they all came from the same binomial data generating mechanism, would be 0.0308. Those give retrospective control limits for p hat by plugging this 0.0308 into the standards given formulas. And one then gets lower and upper control limits given on this slide. If you then use those control limits and look at the data retrospectively, it's still the case that that sample 9 is seen to be inconsistent with the others. It's just not plausible that those counts all came from a single binomial data generating mechanism. It's worth noting here that the lower control limit for a p-chart can be positive. There is a lower control limit that's bigger than 0. That means it's possible to get a p-hat that is too small. Well, that causes some consternation, some head scratching for some people, thinking, well, but I want p-hat to be small. One has to remember that the point of control charting is about detecting process change, not about product acceptability. And so if I get a point that's below a lower control limit on a p-chart or an NP chart, what I conclude is that somehow, for some reason, there is process improvement indicated. And one would like to follow up and know why that happened. And so one needs to be alerted to that. And that's exactly what a positive lower control limit on a p-chart does for one. It allows one to follow up on surprisingly small values of p-hat or of x. Sometimes sample sizes vary. The control limits for p-hat and x depend upon the sample size, and basically one needs to recalculate control limits if the sample sizes change. A slightly counterintuitive, but not really counterintuitive truth is that large sample sizes for a p-chart produce control limits that are tight around the center line. So the more informative that a sample is, the less variation that one allows in p-hat before one says, oh, not at a standard value. And so it's not really surprising that using, say, a standard of 3 in 100, that the sample size, that the control limits for a sample size 100 are wider than our control limits for sample of size 400. We'll talk next in the next module about control charts, not for fraction non-conforming, but rather mean defects per unit.